So this is going to be part 3 of our video on intermolecular forces of attraction. And so in this part of the video, we're going to talk about equilibrium between some of the various phases: solid, liquid, liquid gas, and so forth. So let's first talk about liquid gas equilibrium. Okay, we'll talk about what equilibrium is in a minute. So vapor is able to escape from the liquid, from a liquid, even if you're below the boiling point. Okay, you know this from practical experience. For example, if you have hot water, let's say if you have just water and you leave it sit outside on a hot day, it will slowly evaporate to dryness, even though even the hottest July day, the temperature never gets anywhere near the boiling point of water. So if open to the atmosphere, the vapor escapes, and the liquid slowly evaporates with time. Okay, now, if the flask is closed, the vapor cannot escape, and an equilibrium is established between the vapor and the liquid. Okay, which of course begs the question, what's an equilibrium? And this is really a separate topic, and there's a whole chapter on it devoted to this later in the semester. We'll cover later in the semester. But an equilibrium is where you have two opposing forces occurring at the same time and at the same rate. Okay? So for example, if we have a sealed flask, let's say we have a sealed flask like this, sealed flask or container of some sort, and we have some liquid in there. Let's say the liquid is water. Well, even if we're not below, even if we're below the boiling point, there's a certain number of those molecules that are going to escape to the liquid surface, or escape from the liquid, okay, and form gaseous molecules. But then at the same time, that's only going to go to a certain extent, and then what's going to happen is the gaseous water molecules will start condensing back down to a liquid again, and that's when the equilibrium is established. Okay, so an equilibrium is when you have two opposing processes occurring at the same time and at the same rate. And in this case, we're talking about evaporation and condensation. So once the equilibrium is established, the number of molecules in the vapor state doesn't change. That doesn't mean that this is a static or frozen situation. It doesn't mean that nothing is happening, but it means is these two processes are occurring at the same time once the equilibrium is established. So for every molecule of water that escapes from the liquid and goes into a gas, we have another molecule in the gaseous form condenses and goes back into the liquid. So the number of molecules doesn't change. Okay? Number of molecules in the gaseous state. So the equilibrium vapor pressure then is the pressure of the vapor at this temperature. At some temperature. Or I'm sorry, the vapor pressure, the pressure of the vapor at equilibrium. So what are some of the factors that affect the equilibrium vapor pressure? See, not all substances have the same vapor pressure. It's very much a function of the strength of the intermolecular forces of attraction. Okay? So stronger intermolecular forces mean lower vapor pressure. Okay? So for example, we look at water. Now we talked about water in the past videos. Okay, we know that water is polar right? It's polar, and it can hydrogen bond. You have strong intermolecular forces of attraction, right? So as a result is you have low vapor pressure, right? So the stronger the intermolecular forces of attraction, the lower the vapor pressure. So if the molecules are stuck together in that liquid state really, really, really well, then molecules are going to have a harder time escaping from the liquid and going to the vapor. Okay? On the other hand, if we look at the other extreme and we compare water to hexane, which is a hydrocarbon and it's a component of gasoline. Now, hexane is very much nonpolar. Okay? Being a nonpolar molecule, it has weak intermolecular forces of attraction, and so as a result, it has a high vapor pressure, meaning that it evaporates readily. For example, if you've ever worked with gasoline, pumped gasoline, let's say you're putting gas in your car or in a lawnmower, let's say you spill some of that gasoline on the concrete, on a pavement, and you watch, and it evaporates very, very, very quickly. It's gone, poof, and it'll be gone, evaporated, where something like water is going to stick around for a long time, right? So strong intermolecular forces amounts to a low vapor pressure, right? And weak intermolecular forces amounts to a higher vapor pressure, right? Because the molecules are less tightly held together or less attracted to one another. All right, so that's one thing that can influence your vapor pressure, the strength of the intermolecular forces. Okay. Second thing is temperature. All right, so vapor pressure increases with increasing temperature, which makes sense, right? Because what are you doing when you heat something up? Heat's a form of energy. When you heat a substance up, what are you doing? You're giving the molecules energy. They're moving faster. The molecules have more kinetic energy. If the molecules have more kinetic energy, they're more of them are able to break free of the liquid state, right? So you heat something up and the vapor pressure increases. So water, let's say, will evaporate much more quickly at, let's say, 50 Celsius than at 25 Celsius. Okay? Now, what's special about the boiling point? So let's say we have water. We're heating a sample of water, okay? And we start heating the water up, and you heat it up to 50 to 60 to 70, 80, and you get up to 100, and then it starts boiling, and you get these bubbles of vapor coming off. What's really happening here? What's happening at that boiling point? Well, the boiling point, what's the definition of boiling point? It's the temperature at which the vapor pressure equals external pressure. Okay? So if you were dealing with something that's open to the atmosphere, let's say we're just boiling something off in a beaker, then your external pressure is atmospheric pressure. So what happens at 100 Celsius with water? 100 Celsius is the temperature where the vapor pressure of water becomes 1 atmosphere. Okay, that's where it becomes 1 atmosphere. Now, you can make the water boil at a different temperature by changing the pressure. If we go back to our sealed system, let's say, if we hook this up, we could actually make water boil. It would be hard, but we can make water boil at room temperature. How would we do that? We'd hook it up to a vacuum pump and suck the air out and reduce the pressure over the surface of the liquid, and the water would boil at a lower temperature, right? Because one more time, boiling happens when the external pressure equals the vapor pressure, right? If this flask is open, let's say we're dealing with an open flask, the external pressure is 1 atmosphere. In other words, if we have we have an external flask, let's say, and now we have 1 atmosphere of pressure pressing down on that flask. Water, one more time, the water boils at 100 Celsius because that's the point where the vapor pressure equals atmospheric pressure, or an atmosphere. Now, if we hook a vacuum pump up, if we're sealed and we hook a vacuum pump up and we suck the air out, we can make the water boil at a lower temperature because we're reducing this pressure. When we suck the air out, we're reducing the flask is closed, and we suck the air out, we're reducing the pressure on the surface of the liquid. Then, of course, the reverse is true. Okay, let's say we have a sealed flask or a partially sealed flask and we start to heat it, then the pressure inside is greater than 1 atmosphere, and we can make the water boil at a higher temperature, right? And that's how pressure cooker works. How is a pressure cooker able to cook foods faster? It makes the water boil at a temperature over 100 Celsius because it's partially sealed and the pressure builds up inside the flask. So now the pressure coming down on the surface of the liquid is greater than 1 atmosphere. So the water is going to boil over 100, right? So the water boils at 100. Water boils at 100 Celsius only at 1 atmosphere of pressure. Okay. So the boiling point is the temperature then at which the vapor pressure equals the external pressure. If you're open to the atmosphere, it's atmospheric pressure. Okay. Now, what's called the clausius-clapeyron equation, that relates temperature, vapor pressure, and heat of vaporization. And that's this equation, that the natural log of the ratio of 2 vapor pressures is equal to the negative of the heat of vaporization over R times 1 over T2 minus 1 over T1, which is kind of a formidable looking equation, but it's really not that bad. You just have to be careful how you set it up and pay attention to your signs. Alright, so R in this equation, R is the gas constant in units of 8.314 joules per Kelvin mole. P1 and P2 are the vapor pressures of your substance at T1 and T2. And T1 and T2 are the temperatures at P1 and P2. Okay? And the temperatures must be in Kelvin. It will not work if the temperatures are in Celsius. Okay? So, let's work a problem. Alright? So let's say at 34.1 Celsius, the vapor pressure of water is 40.1 torr. Okay, and we want to know what is the vapor pressure at 85.5 Celsius. And if the heat of vaporization of water is 40.7 kilojoules per mole. So let's look at what we're being given. We're being given one temperature and one vapor pressure. And we're being given the heat of vaporization, and we want to know what is the vapor pressure at 85 Celsius. So we're solving for a pressure. Okay? So we'll let T1 be 34.1 Celsius and T2 be 85.5 Celsius. Now, we have to convert that to Kelvin, right? So we add 273 to that. That's 358.5 Kelvin. Okay. Pressure is 40.1 torr. And P2, we don't know. That's what we're solving for, right? We know it at 34.1 Celsius. The pressure is this. What we don't know is the pressure at 85.5 Celsius. That was what we're solving for. So, natural log of P2 over P1. The P2 is what we're solving for. So P2 over 40.1 is negative 40,700 joules per mole over 8.314 joules per Kelvin mole times 1 over 358.5 minus 1 over 307.1. Now, how did 40.7 become 40,700? Because this is kilojoules per mole, and our gas constant is in joules per mole. Okay, that's in joules per mole. So to keep the units constant, I converted kilojoules into joules. Okay, so what I next did here, everything is the same, is copied it over, except I evaluated the 1 over 358.5 minus 1 over 307.1. And that comes out to be negative 4.67 times 10 to the minus 4th Kelvin. Okay, and then I evaluated this whole thing, so we have a negative times a negative, that becomes a positive. So 40,700 divided by 8.314 times negative 4.67 times 10 to the minus 4th. And this comes out to be 2.286. So the natural log of P2 over 40.1 is 2.286. Well, what do we do? What do we do here now? We got to get rid of that natural log. Okay. We can't just say P2 over 40.1 is equal to 2.286. That's not what this says. It says that the natural log of P2 over 40.1 is 2.286. Now remember that with algebra, you can do anything. You can do anything to an equation as long as you do the same thing to both sides. We can add to both sides, we could subtract from both sides, we could multiply both sides by a number, we could divide both sides by a number, or we could take the log of both sides, or we could take the natural log of both sides, right? So what we're going to do here is we have to get rid of this natural log. So what are we going to do? We're going to take the inverse natural log of both sides of the equation, right? So the inverse natural log of the natural log is just the number itself. So by taking the inverse log, we're getting rid of the natural log. Okay, so really then what we can say is P2 over 40.1 is equal to the inverse natural log of 2.286. So how do we do this on your calculator? Now your calculator is likely going to be different, but you see here's your natural log function, and then there's a second function for the natural log that's basically e to the x. Taking the inverse natural log is the same thing as taking e to the x. So we take 2.286 okay, so we take 2.286 and we take second function, so basically that's inverse natural log, and you get 9.8355. I rounded it up to 9.84, and now it's just a matter of algebra. So 9.984 times 40.1 is 394 torr. Okay. Now first, ask yourself the question, does this make sense? Always try to check and see if your answer makes sense. How would you know this answer makes sense? Vapor pressure increases with increasing temperature, right? So at 34.1 Celsius, our vapor pressure is 40.1 torr. We're going all the way up to 85.5 Celsius. There's a pretty significant increase in temperature, right? So the vapor pressure should go up. Our answer should be greater than 40.1 torr, which it is. Okay, so we're going up from 40.1 torr to 394 torr. And that's the clausius-clapeyron equation. That's how you use it. Now, basically, anything could be a variable here. So for example, I could give you two different vapor pressures and two different temperatures and have you calculate the heat of vaporization. Or, if you know the heat of vaporization and you know one pressure and one temperature, you can calculate the pressure at a different temperature. That's what we just did. Or you could say, okay, well, what the temperature or the pressure could be a variable you're solving for. You could say, okay, at what temperature would you have a vapor pressure of 760 torr? So let's go to solid liquid equilibrium. Not as much to say about this. Remember that freezing and melting is the equilibrium between a liquid and a solid. Now this varies very little with applied pressure. Okay, you will not change the freezing point of water very much by changing the pressure. You can change the boiling point a lot, but you can't really change the freezing and melting point. Okay. Solid gas equilibrium, sublimation, deposition. Okay, that's the equilibrium between a solid and a gas, right? Sublimation is solid to gas, deposition is gas to solid. Okay. I will say this, that many solids can be made to sublime, just not under ordinary conditions, right? The most common example is dry ice, which is the most common example of something sublimes is dry ice, which is frozen carbon dioxide. At room temperature, or atmospheric pressure rather, it goes from a solid directly to a gas without going through a liquid state. I've seen things, packed in dry ice to keep them cold during shipment, because it doesn't melt and make a liquid mass. It goes directly to a gas. But many solids can be made to sublime, just not under ordinary conditions. Okay, what we would have to do is change the pressure, and most likely, greatly reduce the pressure. Just like, for example, we could make water. You can make water boil at a lower temperature by reducing the pressure. You can also make ice sublime by reducing the pressure, but you have to go to a really low pressure. All right, this leads us to phase diagrams. Okay, so a phase diagram is a graphical representation of the pressure temperature relationships that apply to the equilibrium between the phases of a substance. So this is a fancy way of saying that we have pressure on this side and we have temperature on this side. All right, and so we pick any combination of temperature and pressure, okay, and that will tell you whether your substance is a liquid or a gas. Now, right, so this is a phase diagram for water. All right, so for example, we see here then that let's say a temperature of 25 Celsius, which would be right around here, that's room temperature. We see that at most pressures, water is going to be a liquid. Okay, and note the scale is not linear, by the way. From 2.4 to 4.4 to much bigger difference between here and here than between here and here. Okay, so that scale is not linear. All right, but anyway, so at any given temperature, in any given combination of pressure and temperature, that'll tell you whether your substance is solid, liquid, or gas. Okay. So curve AB is called the vapor pressure curve for the solid. Okay, so at every point along the curve, ice, because we're using water as an example, ice and its vapor are able to be in equilibrium. Okay, so that's this curve right here. Okay, that is the vapor pressure. That's the vapor pressure of the solid. Because what do you have on one side of this curve, right? You have solid on one side and you have gas on the other. All right, so this basically tells you the conditions of temperature and pressure under which ice could sublime. And the pressure would have to be really, really, really low, like below 4.58 torr. So let's say our pressure is here, and as we increase and as we move here, as we increase the temperature, we start out as a solid, and as we increase the temperature, we can go from a solid directly to a gas. But if we're above 4.58 torr, let's say we're at 330 torr, and we increase the temperature, and we start out as a solid, then we go through a liquid state before we get to a gas. So anyway, curve AB, from here to here, you have solid on one side, gas on the other. That's the vapor pressure of the solid. Okay, curve BD, okay, that is the vapor pressure curve for the liquid. This gives the temperature and pressures at which liquid and vapor are able to be in equilibrium. All right, so that's this curve, correct? That's this curve right here, right? So on one side of this curve you have liquid, and on the other side you have gas. Okay, so basically points along this curve will tell you the boiling point of the liquid. So for example, 760 torr, you should remember from Chem 1, pressure of 760 torr, that's 1 atmosphere, right? So at 760 torr, water has a boiling point of 100 Celsius. Now remember what I said about how you could make water boil at a lower temperature by decreasing the pressure over the surface of the liquid, hooking up the vacuum pump and sucking the air out. Let's say at 330 torr. Now we come across and we come down to 330 torr. Now what's our boiling point? It's only 78 Celsius. Okay, but it's important to note this curve is not linear. It's a logarithmic curve. And basically that's what we're doing with the clausius-clapeyron equation, is calculating various points along this curve. Okay, so again, you could make the water boil how a pressure cooker works. We could make the water boil at a higher temperature by increasing the pressure. So if you're over 760, let's say, now your boiling point is going to be greater than 100. Okay, so anyway, curve BD, that's the vapor pressure of the liquid. All right, point B is called the triple point. Okay, so that's the point at which you can have liquid, solid, and vapor all in equilibrium at the same time. Okay, so for example, that's point B, that's right there, that's the triple point. So for water, that happens at 4.58 torr and 0.01 Celsius. That's the triple point. All right. So point D, that's all the way out here. Okay. Point D, that's the critical point. Okay. So that's the point at the end of a vapor pressure versus temperature curve for a liquid that corresponds to the critical pressure and the critical temperature. Okay. So the critical temperature is the temperature above which a substance cannot exist as a liquid regardless of the pressure. Okay, so beyond that temperature, it can no longer be liquefied. Okay, that's the critical temperature. And then the critical pressure is the vapor pressure of a substance at its critical temperature, or the temperature required to make it a liquid at that temperature. But beyond that temperature, it cannot be a liquid. Okay, it's a critical temperature. And that pretty much wraps it up for this chapter.